Hello friends, welcome to this tutorial on the transformer architecture in natural language processing. This is based on the paper Attention is All You Need, which serves as the foundation for the working of ChatGPT. There are many tutorials and learning materials available on the internet about transformer architecture and its internal working, but mostly explaining the concept theoretically using blocks and diagrams. From that, it is difficult to understand the data format, data manipulation and transformations, and its flow from one component to another. Today, our objective is to explore each component of the transformer architecture and implement them individually using Python. My intention here is not to build a fully functional transformer model, but to understand each component in detail and implement a base model using Python and then analyze the input and output data transformations. The transformer architecture was introduced in a research paper, Attention is All You Need, in 2017. It revolutionized the field of natural language processing by replacing recurrent neural network with a self-attention mechanism that allows parallel processing of input sequences. The transformer was originally designed for machine translation task. That means translating a language to another language. It consists of an encoder and a decoder. The encoder processes the input sequence while the decoder generates the output sequence. During model training, the encoder is fed with a sequence of words in one language, and the decoder is provided with the corresponding word sequence in the other language. For example, if you intend to train the transformer model for English to French translation, the decoder will fed with English sentences and the decoder will input the corresponding French word sequence during training. Both the encoder and decoder consist of multiple layers, each comprising sub-layers. Let's start looking at the encoder internals. Here is the encoder part of the transformer. In real implementation, there will be stack of encoders comprising the encoding component. The decoder component is a stack of decoders of the same number. I have taken this picture from Jay Alamar's blog about transformer. He has beautifully explained its working. Let's begin with the inputs. In this architecture, the first step involves converting the inputs into input embedding. The transformer architecture was initially designed for language translation, so the inputs are a series of words. However, machine learning models can only understand numbers. That's why we need to convert these words into numerical representations. That's where the embedding layer comes into play. Word embedding is a technique used to represent words as dense vector representations in a continuous vector space. In this representation, words with similar meanings or semantic relationships tend to have similar or closer vector representations. There are many libraries available to create vector representations of words. Some of the popular libraries are Gensim, Spacy, FastText, Glove, etc. Word embedding relies on distributional hypothesis, which states that words that appear in a similar context tend to have similar meanings. This scatter plot representation of words in a vector space has been created using Gensim library. I have used some research papers content as input to this word embedding model. Let me zoom in on some areas that appear crowded to observe the words that are close together in the vector space. You need to remember here that these tokens are represented using 100-dimensional vector space, but we are plotting those on a 2-dimensional space here. Seems like these are mostly nouns. In that also, here people names are clubbed together: Martin, Robert, Peter, Alexander, Agarwal, etc. And here country or place names are plotted in nearby spaces. Similarly, words with a similar meaning or semantic relationship have close vector representations. Take another space. Connections, connectivity, etc. Here seems like words related to wave or signal. Just zooming in one more vector space. Hope you got an idea behind the word embedding now. I will demonstrate the Python code for generating word vector representations. By the way, Spider is my favorite IDE for machine learning projects. You can easily install Spider using Anaconda Navigator. Deleting all the variables. The word2vec function from GenSim library has been used here to create vector representations of words. I am downloading a few resources from NLTK library. This will download a corpus of stop words, which are commonly used words that are often removed from text during preprocessing. This command downloads the WordNet corpus, which provides lexical information and semantic relationships between words. OMW is Open Multilingual WordNet, which is an extension of WordNet that includes multiple languages. We need to perform data cleanup and pre-processing tasks such as converting text to lowercase, removing punctuations and stop words. After removing the stop words, the words are lemmatized. That means reducing the words to their base form. Running these lines of codes, this is taking long time, so I am fast forwarding. Then creating the tokens by calling word tokenize method from NLTK library. The result object is of type panda series. This contains sequence of words from each document. Let me open this series object to take a closer look at the token data. There are total 7,241 documents. These arrays contain a lemmatized words from each document. The number of tokens from each document may vary. If you want to identify the documents with a maximum number of tokens, you can use a lambda function to get max length. By executing these two lines, you will obtain the max length. I am getting that as 9385. To access the elements corresponding to the maximum length, open max length elements. There is only one document located at index position 5966 in the data frame. That has the maximum number of tokens. The same way you can find minimum number of tokens and other statistics also. Then converting these tokens into word embeddings by calling word2vec method. The main parameters we are passing to this function are tokens. MinCount specify the minimum frequency threshold for words to be included in the vocabulary. Window sets the context window. Vector size default value is 100. This represents the output vector dimension for each word. Executing this word2vec method, the object has been created. This is our tokens series object. Just pick a word from it. For example, if you want to see the word embedding for computation, use model.wv.getVector method and pass the token. Here is the vector representation for the word in a 100-dimensional space. In the original transformer architecture paper, it is specified that 512-dimensional word embedding vector has been used. In our example, everywhere I am using 100-dimensional word embedding vector. I believe now you have a good understanding of the term word embedding. In NLP, there are other methods to represent words such as one-hot encoding or assigning a sparse binary vector to each word, where each dimension of the vector represents a word in the vocabulary. However, these representations lack the ability to capture the meaning and relationships between words effectively, creating a word vocabulary and corresponding embedding vector for each word. This list contains all the unique words used across all the documents. There are 2771 unique words in the vocabulary. This embeddings list contains corresponding vector representation of the words. This piece of code has been written to plot word embeddings in a vector space, generating a scatter plot visualization, which I already have explained. And finally, to show the word embedding representation for input sequences, this code takes the first 5 records from the input token matrix and replaces the token with their corresponding word embedding vectors. Outer loop is responsible for taking the first 5 documents, and the inner loop iterates over each word in the sequence. Running this code segment, after execution, we have this input embedding array consisting of 5 rows, each having list of embedding for each word. The word count varies in each sequence. Here is the embedding vector of size 100 for each word in the sequence. This word embedding matrix will be passed to the next layer where positional encoding information will be added. Next stage is positional encoding. The purpose of positional encoding is to add some information about the order of words in a sequence to the word embeddings before feeding to the encoder or to the decoder. The transformer architecture was created for NLP task like language translation, where order and relative positions of words in a sequence are crucial. The transformer model, however, does not use recurrence or convolution and treat each word or token independent of the other. Since the word embedding do not consider the order of words in a sequence, positional encoding helps to provide the model with information about the relative positions of words in a sequence. A common approach for positional encoding in transformers is to add position-specific information to the word embeddings. This positional information is usually represented as additional vector values that combined with the word embeddings. The positional encoding vectors in the transformer model was generated using a mathematical formula based on sine and cosine functions. In order to understand the concept, I will show you the visual representation of positional metrics and vector values corresponding to different positions. Let me go back to the coding. Clearing all the previous variables. This tiny function implements positional encoding logic using sine and cosine functions. Input parameters to this function are sequence length and dimension. This dimension should match with the word embedding vector dimension. For odd position vector space for a word, it will use sine function, and for even position, it will use cosine functions to calculate the position value. Consider an example string input. Natural language processing is excellent. In the data pre-processing stage, the stop word is will be removed. Now we have 4 words or tokens in this string. Using the sequence length 4 and output vector dimension 100, generate positional encoding matrix. Let me run these lines of code. Now, in this positional encoding matrix, we have 4 rows corresponding to each word and 100 columns. In fact, the positional encoding matrix would be same for any 4-word sequence with a dimension of 100. That means it is independent of the input string, only considers the sequence length. Consider this first vector for the word position 0. This column number can be considered as index I and the row number is the word position in the sequence. Here the word position is represented by the value pos. Sine function is used for odd column numbers and cosine function for even columns. So in the first column, when pos equals 0, sine 0 is 0 and second column cos 0 which is 1. It is repeating again and again because the numerator here is 0. So it is repeating the values 0, 1, 0, 1, 0, 1 and so on. For the second word position, pos is 1, d is again 100 and I starts from 0 to 49. One thing you may have to notice here that the outer for loop iterates for all the words in the sequence, but the inner for loop, which is for the vector dimension, iterates only half of its length. This is because each iteration it is creating 2 values, one for sine and the other for cosine. The value for d should be always an even number. In the original transformer paper, the vector size has been selected as 512. This positional encoding matrix will be added to the word embedding matrix to retain the information regarding the order of words in a sequence. You may still wonder how this combination of sines and cosines could ever represent a position or order. Let me go further into the positional encoding logic. Let me plot the sine wave for different word positions. Here is a function to plot sine wave for different position parameters in the scale of 0 to 100. 0 to 100 with d equals 512. For the y-axis, I am setting the value used in the positional encoding function. Adding a pause of 500 milliseconds to reduce the plotting speed so that it will be more visible and clear. Plotting the sine function for the position values 0 to 100. For word position 0, it is a straight line having value y equals 0. And for position 1, we will get a very high wavelength and a low frequency sine wave. We can notice here that as we increase the position value, frequency of the sine wave increases and wavelength decreases. This means that you will get a unique sine wave having consistent behavior and values within the range of -1 and 1 for each word position in a sequence. Because of these characteristics, you have a way of measuring or quantifying the similarity between different positions, hence enabling you to encode the relative positions of words. You will get a similar result using cosine function also. And finally, let me plot the positional encoding matrix derived using combined sine and cosine functions. Calling getPositionEncoding function, the input sequence length used as 50 and the output vector dimension is 100. Used matchShow function to plot matrix as color-coded image. Here the sine and cos values have been represented using color intensity. Let me place the matrix and its plot side by side. Each row is corresponding to the word position in a sequence. In the first row, we have only zeros and ones that you can identify clearly in the plot also. When the position value advances, we have different values in our vector, and hence each word position in the sequence is uniquely identified using the corresponding positional encoding vector. We have the word embedding matrix having the same dimension, and this corresponding positional encoding vector will be added to the word embedding to inject the positional information. Spider is also applying a default color gradient depends on the cell value. From the changing color intensity, we can notice some pattern it is following. If you change the sequence length and dimension, you will get a similar plot. Just changing the sequence length to 100 and dimension as 512. See, the plot generated is identical. I hope you have a better clarity now about the working of positional encoding. So far, we have done only data pre-processing parts which we need to do only once, required for encoder and decoder.